we have a look at statical determinacy. Okay. So next we want to look at how to draw shear force diagram and bending moment diagram for frames. So shear force diagram, bending moment diagram for frames, it is part of the important design process because we want to know where is the maximum shear force, where is the maximum bending moment, and how do they change along different parts or different members of the frame. Okay, so the procedure is the same like what we used for beams, but because of the additional the characteristics of frames which we do not see in beams, so there are additional calculations. So in beams, normally we do not need axial force diagram because normally axial force in beams are 0 because the loading is primarily, mainly perpendicular to the axis and is not going to cause axial force. But in frame, we have additional diagrams that we have to draw other than shear force diagram, SFD, bending moment diagram, BMD. We have this AFD, okay, axial force diagram, or sometimes we call that the thrust diagram. The thrust is like axial force acting along the axis of the member. Now, before we proceed to the process of getting this axial force, sometimes we use N, sometimes we use Q, okay? So the important thing is understand what is the definition of axial force. The symbol can be Q, can be N. And a symbol for axial force, we can use it as S or V, okay? And bending moment is M, okay? So the first thing that we need to get hold of, understand correctly, is the direction of actions of axial force, shear force, and bending moment, and the corresponding positive directions. In beam, it is easier because beam members is only oriented horizontally. But in frame, you have member which is vertical and horizontal. So how do we define this on different horizontal and vertical members? So here I show you two members, a frame with two members, one vertical, one horizontal. So the first thing that we have to take note is we have to indicate the axis of the member, which is pointing from one end to the other. So the X is for this member, X prime is for this member. Then if we cut through, when we want to talk about axial force, shear force, or bending moment, you have to cut through the members. Only then they appear. Okay? When you don't cut through, they don't appear. So when you cut through these, then appear axial force, shear force, bending moment. When you cut through here, this horizontal member, then you get axial force, shear force, and bending moment. So the directions, the definitions of axial force is the force which is parallel to the sections. So the section is defined as perpendicular to the axis of the member. The section of the member of this cut is defined as perpendicular to the axis. Here also perpendicular to the axis, so 90 degrees. Here also 90 degrees. So on this section which is perpendicular to the axis, we define axial force as a force acting parallel to that section, perpendicular to that section, and shear force as parallel to that sections, and bending moment. Okay. Here also a force which is perpendicular to the section, and then this S is parallel to the sections, and bending moment. So this is how we define. We define with respect to section perpendicular to axis of member. That is the first thing that you have to recall. So it is defined with respect to section perpendicular to axis of member. Okay, so this is axis of the member, so it is defined perpendicular on the section perpendicular to that axis of a member that I show with the red color here now. If you have inclined members, then the same thing. Yeah, the axis is like this, so the Q, S, and M is defined on the section which is perpendicular to this axis. So the direction here becomes different now. If you compare this and this, different now. the Q, S, and M. So take note of that. That is an important thing. Where are the directions being defined? Okay. So with that understanding, then let's go to the one example, just to illustrate to you the process and the calculation process involved to get the shear, bending moment, and axial force diagram, and the qualitative deflected shape for the frame shown in this figure here. So this is a frame, 3 members frame, vertical member AB, horizontal member BC, and another vertical member CD, 10 meter, 10 meter, 7 meter, pin support, roller support, and there is a concentrated load here, point load here, 10 kilonewton at B, and there is a uniformly distributed load, 5 kilonewton per meter along member BC. So the process that we are going to go through is basically the same. Okay, the first thing, you get the reaction force. So if you ask to check statical determinacy, also you check statical determinacy. So this is, we use the method that we have just gone through, cut it here, then cut one section, three internal forces appear, reaction forces, they are 1, 2, 3. So total number of unknown forces 6, equilibrium equation 3 here, 3 there, 6. So statically determinate. So it's easy, okay? Or like this. So because there's no closed loop here, we actually don't need to go through this process. No need to use this method. So the next is same like the case of beam. Calculate the reactions. Calculate the reactions. So we have 3 reaction forces. So we have to calculate reactions. So in some cases, when you go through enough example, we do not need to calculate all. Yeah, we might just need to calculate AX, AY, then we can start the process of getting axial force diagram, shear force diagram, and bending moment diagram. Sometimes we can just need to calculate one reaction force D here. Then we can start. Okay, but it normally in most cases you have to calculate at least some of the reaction forces before you can start with calculating getting the axial force diagram, bending moment diagram, or shear force diagram. So this is just a refresh. So try to get the reaction forces by using the 3 equilibrium equation that we have. So this is important steps, and because this is the first step, if the first step is wrong, then the rest of the axial force diagram, shear force diagram, bending moment diagram, and also qualitative deflected shape might be wrong as well. Okay, so try to be very clear about the process of getting reaction forces and the moment. Don't forget what is moment. Okay, so this is the first step. So next we calculate, we get the shear force and bending moment at different sections, at different parts of the frame by cutting through the members. We use the cut section method. We use a cut section method. So how many cuts that we have to do? So the first rule is for each member here, A, B, B, C, and C, D, there are 3 members, at least you have to cut once. And if along that members the load is changing, then you have to cut more than once. Okay. For this example, we have AB here, there is no loading, so we cut once is enough. So anywhere you can cut here, 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 as long as it is a section in general representing any section along this member AB. BC, and only one loading here, so once. If this loading does not extend until the end, is only halfway here, then you have to cut 2 times. One through the loading, one where the location there is no loading. And the third member CD here, no loading along here, so we cut only once. So determination of number of cuts required. Okay. Then after that, you go to each of the cut one by one, get the free body diagram, then calculate the shear force and bending moment, okay, one by one. Then finally, combine them, you get the shear force diagram, bending moment diagram, and later on, axial force diagram for the frame. Okay. So next, after you cut this, then you show the positive directions of shear force, axial force, and bending moment, or Q, S, and M. Okay. Now, how to determine this? I will come to this. I will come after later this when we go through this example. How do you define the positive Q, positive S, and positive M for member AB, BC, and CD, or for any other example? Okay. For the time being, please take this as the positive direction when you cut through here, positive Q, positive S, positive M. When you cut through here, positive Q, positive S, positive M. When you cut through here, and then when you use section on this part, positive shear, positive Q, positive shear, positive M. After this, I will explain how do we define this. So ready? Next, go through at each of the cut sections one by one. Then when you cut through this part here, section AA, this frame will be separated into two parts. Two parts here, same like a beam. So you choose which part you want to use and you draw the free body diagram. So here, when we cut the frame at this section AA here, this frame is separated into this part and the other part that's shaped like this. So we choose the part which is involving less force and easy to calculate. So we choose this part here. After cut, we choose only this part down here. Okay? We choose this one. So this is a free body diagram. And here the Q, the Q should be here, but we ignore the Q, just take away the Q just to avoid this being too congested here. So there should be a Q here, okay? So we just don't draw the Q here for simplicity, okay? So now we have, this is the free body diagram for this part. So when you cut through, there must be a shear force bending moment appear. So now we indicate this as X, this as Y, and shear now is pointing in X directions. So we use equilibrium equation of forces in X direction to find shear S. So from this diagram, we found that S is equal to 10 constant. So starting from here, after you get this, it is an application of equilibrium equations. So we have to take note for vertical member like this, if we use reaction, we use the coordinate axis like this, X and Y. So S is now pointing in X direction. So we have to use the equilibrium of forces in X direction like this. Bending moment, take bending moment at the cut section here. Take bending moment at the cut sections. So we have M equal to 10 multiplied with X, a straight line here. So this is applicable for A to B. So X is changing from 0 to 10. So if you draw the shear force and bending moment, then we will get, this is the AB, so the shear force positive, so we draw here. Bending moment is a straight line, starting from 0 until 100. We draw on this side here, positive. Where should we draw? Again, I will explain after this, where should we draw when we talk about the positive direction of Q, positive direction of M, and positive direction for S, and where should we draw? If it is positive A, positive shear, positive M, where should we draw? So next cut, repeat the process. So we cut this frame is separated into two, so we make use of this part here. So this is a free body diagram. Again, Q we ignore here temporarily. So S and M, this is the positive directions. So if I take X and Y again like this, so summation of forces must be taken in Y direction now to get the shear. So the shear now is, because there are distributed load involved here now, so the shear become a straight line. This is application of equilibrium equations. Okay. Then bending moment, take bending moment at the cut section here. So we get M must be equal to M plus this, okay, and this one not causing any moment, then minus this one, yeah, 15 multiplied with X, and then 10 and 10, this form a couple, so 10 must be considered here, must be considered when we evaluate bending moment. So this is just equilibrium equations, okay. Then we get M is equal to X squared now, because the bending moment here involves UDL, so it is X squared. It's a curve now. It's a curve. So this is again applicable to B to C, so X is from 0 to 10. So the same thing next, finally, the third cut. But before that, if you draw here, then this is a shear force diagram, straight line, and this is a bending moment diagram, which is a curve. Again, when we have zero shear, whenever we have zero shear, then we will encounter a maximum or a minimum point in the bending moment diagram, and we have to calculate that. To calculate that, we need to determine the location first. And to determine the location, we treat it like a beam here, and we use the relationship between loading diagram and the shear force at point B and point B prime and point B. So shear this minus this shear is equal to area under the loading diagram. So we get these equations. From here, we solve for this. After this, you substitute into these equations to get what is a moment here, which is 122.5. Or you can use the similar triangle over this is equal to this over this. You can also calculate XB prime here. So this is how we draw. This is part BC, part BC. This is how we draw, positive here, negative here, positive on the top part here. So after this, the last part, this one just to whether we should curve like this or curve like this, because curve X squared can be curving like this, it can be curving the other way around. So remember, we make use of these relations between slope in bending moment diagram equal to shear at the same point. So this is positive shear, so the slope is like this. Zero shear, so horizontal slope here, maximum point. After this, negative shear, all the way increasing, so this one should be, that's why it should be curving like this. Yeah, or we look at, there's a negative in front of X squared here, so it should be curving up in this way. Next is the complete. So we have the final section here, we cut through here, final section we cut through here, then we separate the frame into two. So we make use consistently like what we have done for the other two cuts. So we make use of this, the section before the cut. So we make use of this large section here. Then if we take X and Y again, the same coordinate axis, X and Y. So X, S now in X directions. So make use of equilibrium equation of force in X directions, get S. It comes up to be 0. No shear along this member. Take moment at the cross section, at the cut section here. Consider all these forces and loading of moment at this point. Then we come up to be moment also 0. To calculate, so very hard here, very long equations here. Finally get 0. Okay. So moment 0, shear 0. This is for this particular member. We can get this very fast if we take the cut section not on this part here, not this part, but this part here. When we cut the frame at this part, we separate the frame into two portions. One like here, which we have used, and the other one which is here, which is very simple, which we didn't use. But now if we use this here, alternatively, then the free body diagram become very simple. Straight away we get S0, because there is no other forces in S directions, and moment 0. So the calculation is short. So this one we can decide ourselves. So after you solving questions, and then you see which part is easy to use. But one guideline is you choose the part where you see less forces to consider. In this case, obviously this part should be used, not this part here. But you double check, you get the same answer. So S0, shear 0, moment 0 means that is just like this, okay, for this part. And finally, if we combine them, so the shear force diagram become like this. Bending moment diagram become like this. No bending moment here, 0. So this is a bending moment diagram, shear force diagram. For frame, you have one extra diagram, which is axial force diagram. So for axial force diagram, we do the same thing, the same cut here. After we cut this, draw the shear bending moment, this free body diagram. Show only the Q. Okay, S and M by right it should appear, but we omit here because just for simplicity only Q. So this is a positive Q direction. So Q is in Y direction. So we take equilibrium of forces in Y direction, then we get Q negative 15. So Q for this part, negative 15, we draw on this side. Next, repeat for next cut BB there. So BB, when we cut, we get like this. So positive Q is like this. So now it's pointing in X directions. So use equilibrium equation of force in X directions. We get Q equal to 0. Because this 10 cancel out, so Q becomes 0. So when you draw here, 0, nothing. Finally, the third here, through here, and we have experience, use this part here, don't use this part. So we get this and Q, positive Q. So Q will become negative. When we draw here for this part, negative draw on this side here. Okay, so that is how we complete all the 3 diagrams. Shear force diagram, bending moment diagram, and axial force diagram, which is specific for frame. We don't get this in beam, or we call it a truss diagram. So indicate this is axial force diagram, and the unit is here. Qualitative deflected shape, just to complete this thing, if you're asked to sketch qualitative deflected shape, remember our bending moment diagram is drawn on the compression side. So because this compression, this bending moment appear on the top, so the top fiber become in compression here, meaning this left-hand side of this member is in compression. Okay, and no bending moment, meaning that this member should remain straight. It will not bend. It should remain straight. It can move, but it will remain straight. It will not bend because there is no bending moment. Here, joint here is rigid, so it should maintain as 90 degrees, 90 degrees in the deformed shape. This is a pin, so shouldn't move. This is a roller. It cannot move up and down, but it can move sideways. So with that information and with the understanding of what is the positive bending moment and our bending moment diagram is drawn on the positive side, so we get this is the qualitative deflected shape. Cannot move here because this is a pin support, so it should start at the same point. Then this one, this side, this member, this side should be in compression, so it has to bend like this, so that this side in compression. The angle here should maintain, so we draw the angle maintain. This one is in top side, should be in compression, so it should bend like this. Okay. Next, this member, no bending moment, should remain straight, and this angle should remain 90 degrees, and we complete this. This is roller, so we allow it to move, but it cannot separate vertically. So this is how we relate the bending moment to the qualitative deflected shape. At the same time, take note of the support conditions. What is allowed, what is not allowed, and reflect that or represent that correctly in the qualitative deflected shape. So this is just for this top member here. If it is positive, then it bend like this. If it is negative, then it will bend like this. And for this part here, if it is positive, then it bend like this. Negative, then it bend like this. So this is understanding that we need to have about the positive, negative bending moment and how it bends, specifically which side will be in compression. which side will be in compression. So I will stop here for a while. Okay. The next thing that I would like to discuss is, of course,